All right, good morning. This is the rest of the 8.3 notes. So this is where we left off yesterday in the notes. So we have percent dissociation. This is also known as percent ionization, and they mean the same thing, okay? So percent dissociation, it's the amount dissociated as the concentration of the amount dissociated divided by the initial concentration, and we multiply that by 100, okay? Now, from the work that we've been doing with the ice chart and the Ka expressions, the amount that's dissociated is just X. So this is the equation that you want to focus on right here. So percent dissociation is equal to X divided by the initial concentration and then multiply by 100. All right, and then stronger acids will have higher percent dissociations. So they break apart more. So we want to do this example right here. We want to calculate the percent dissociation from the previous problem. So let me switch over. I'll go back and forth between the notes and this Jamboard so I can show the work. But this is that previous problem that was in your notes. We want to find now that the percent dissociation. So from this one, we found X before. X was 1.1 times 10 to the negative fourth. And that's going to be molar. It was talking about a hydrogen ion concentration, so it's molarity. All right, now for the percent dissociation, we just want to carry over that X value. So it's going to be 1.1 times 10 to the negative fourth. And we're going to divide that by the initial concentration, which was 0.350. And we're going to multiply that by 100 to get a percentage. And we end up with, we want 2 sig figs, so it's going to be 0.0, get that decimal point in there, is 0.031%. Okay? All right, so that's how we do percent dissociation. We just take the X value, which, if we're doing a Ka problem, it's just going to be the concentration of the hydrogen ions. So we could get that from the pH. We could anti-log the pH and get the X value. And then we just divide by the initial concentration. All right, but that's how we work with that equation. Okay, switching back over to the slideshow. Just so you know, this equation right here for percent dissociation, this is not on your green equation sheet. So this is just something that we want to remember, okay? All right, next, now in the notes we have another practice problem, another weak acid problem with the Ka value. So I'm going to switch over again to the Jamboard. Okay, so here's that sample problem. So let's start with the Ka equation that we use for weak acids. So Ka is going to be X squared over our initial concentration. We want to put a little subscript 0 here to represent initial conditions. Okay, so on this one we have a 275 milliliters. We know the pH right here, it's 4.82, so it's slightly on the acidic side. We also know the Ka value. So we want to find the initial concentration of HCN, and then we also want to find grams of HCN. Right, so the process here is, if we know the pH, we can anti-log the pH and figure out X. X is the hydrogen ion concentration, so we can take 10 to the negative pH and figure that out. Once we get X, then we know X squared, we know Ka, we can rearrange this to solve for the initial concentration. So that's going to be the next step, is to solve for our initial concentration. And then once we know our concentration, that's going to be in moles per liter. We know the volume right here. So we can convert this into moles, and then once we know moles, we can determine the molar mass and convert it into grams and get our final answer of grams right there. So that's going to be the process. All right, so let's start by figuring out the hydrogen ion concentration, which again in a Ka expression for a weak acid, it's X. So we're going to anti-log this, so this is going to be 10 to the negative pH, and that ends up being 1.5 times 10 to the negative fifth molar. Okay, so that's our X value. All right, now we can rearrange this equation. We solve for HCN, initial. That's going to be equal to X squared over our Ka value. So that's just taking this equation, rearranging it to solve for the initial concentration of this hydrocyanic acid. Then we can put our X value in for here. We can put the K value in right here. And from this we get 0.37. And that's going to be moles. It's molarity, but right now let's write it out as moles per liter to work with the units. And that's one of our answers. Okay, we were looking for the initial concentration of that HCN. There's that one. All right, now we also want to find grams of HCN that are going to be in that solution. So now the rest is just mole conversions here. We want to multiply by the volume of the solution, so 275 milliliters, but we want to convert it to liters to cancel out those units, so 0.275 liters. That gets it into terms of moles of HCN. Now we want to use the molar mass of HCN to get it into terms of grams. So 1 mole of HCN has a molar mass of 27.0 grams. So 1 hydrogen, 1 carbon, 1 nitrogen, those add up to 27.0 grams. All right, so now the units of liters will cancel, the units of moles will cancel, and we're left with grams for our answer. So then we just multiply these three numbers together, and we end up with 2.7 grams of HCN. Okay, all right, and that's that one. That one's all done. All right, I'm going to switch back. Okay, so now we're on to weak bases. Okay, so weak bases, it's the same concept as weak acids. They only partially ionize. They tend to have small Kb values, and their equilibrium problems similar to weak acids. So we're going to have that a Kb expression just like the Ka expression. The key difference is right here. X is going to be the hydroxide ion concentration now when you're dealing with weak bases. All right, so the general reaction for a base in water is right here. We have a base is something that accepts hydrogen ions or accepts protons. So this is your base, and it accepted a hydrogen ion right here, and it turns into, oh, this is, the spacing's bad here. This acid, this Hb plus should be a conjugate acid. Just make sure that's clear on your notes. I don't think I just spaced it right on the slideshow here. This should be, this OH minus, that should be your conjugate base. Okay, so just make sure we get that, make sure that's clear on your note sheet. I think it is, I think it's okay on your note sheet, it's just bad on the slide right here. So anyway, the base is going to turn into this conjugate acid after it accepts that hydrogen ion. The Kb expression is right here. It's the conjugate acid times the conjugate base over the initial concentration of your base. And then we also have pKb equals a negative log of Kb. All right, so we're going to go right to an example right here. We want to find the pOH and the pH of this 2.5 molar solution of ammonia. Ammonia is probably the most common weak base that you're going to see that we're going to work with. All right, that has a Kb value of 1.8 times 10 to the negative fifth. Okay, and I'm going to switch over to the Jamboard again. All right, so here we have that example problem. Okay, so now for the KB expression, so similar to Ka, you want to use this for any weak base equilibrium problems. So you have the KB value is going to be equal to x squared over the initial concentration of the base. So we're just going to represent that with just B with the subscript 0 to represent the initial conditions. Okay. Now again, like I said in the notes, the key difference here is that when we find X, it's going to be our hydroxide ion concentration. Okay, so just make sure we're really clear on that with this KB expression right there. Okay, so now we want to find the POH and the pH in this problem. We know the initial concentration, 2.5 molar, and we know the KB value. So we can rearrange this. We know KB, we know the initial concentration. Let's rearrange to solve for X. So X is going to be, and we'll write it here too, it's going to be the hydroxide ion concentration. And that's going to be equal to the square root of Kb times the initial concentration. So it's going to be 1.8 times 10 to the negative fifth times 2.5. Okay, so the result of this is, get this down here. Okay, so the result of that is 0.0067. Okay, and just like the other problems that we've worked, once we get either the concentration of hydroxide like we have now, or the concentration of hydrogen, or the pH, or the POH, we should be able to find any of those four values. Okay, pH, POH, OH minus concentration, H plus concentration. Again, once we know one of them, we should be able to figure out all of them. All right, so now we want to find, let's find the POH first. So the POH is going to be the negative log of our hydroxide concentration. So it's going to be the negative log of this value right here. That ends up being 2.17. And that's equal to our POH. Okay. Again, 2 sig figs here, so we want 2 decimal places in the POH. Okay, so there's our first answer. The other answer, pH, let's assume it's at 25 degrees, so now we can just take 14 minus our POH. Again, for all these study guide and notes problem, let's assume it's at 25 degrees. So we just subtract from 14 and we get 11.83 for our pH. Okay. All right, and there we go. So that's the end of 8.3. Now in the study guide, that's up through question number 29. Okay? All right, have a good day.